we defined last time, we started this really simplicial complex, and we, if I remember correctly, we stopped when we calculated. Let's make a recall. What's the notation? We look at the final field FQ. V is FQ to the n, and we took the simplicial complex such that the vertices, or if you want x0, is all non-trivial. Non-trivial means neither 0 nor v subspaces of v. There are too many v's. This would be v, the space, and we have a tau function, which is a type function from such w. So the tau of w is simply the dimension of w, and xi, the I simplices, is simply all the sets wi1 inside wi0 inside wi1 inside w of j0, j1, sorry, up to ji, right? Like a flag of I plus 1 subspaces is the set of I cells, and we started to calculate. So we saw that and we call this x, say it is the spherical n q. Okay, this is the flag, and what we saw that S3q is a bipartite graph, bipartite q plus 1 regular graph, which is the points versus lines of projected plane, of the projected plane over FQ. And the eigenvalues in this case were plus minus q plus 1, and plus each one of them with one multiplicity, and plus minus square root of q, each one with very high multiplicity, which we basically can calculate. Now the first really interesting and not completely trivial case is the next one. So let's look. I want to compute it. I hope that already today you will understand why the computation of these eigenvalues is important for us. So let's look at S4Q. So S4Q now, this is the one-dimensional, two-dimensional, and three-dimensional. Now we have three levels. So this is a two-dimensional complex, right? The maximal chambers are of length 3, and it gives rise to three bipartite graphs. The bipartite graph that B12, B13, and B23. So this is 1 against 2, this is 2 against 3, which means the subspaces of dimension 1 against the subspaces of dimension 2. And like actually, yeah, I'm going to compute this, even though there will be, later on we'll need a different interpretation, but I'm sorry, yeah, okay. I prepared this, I didn't think, now I see that if I would look ahead. Okay, they're also relevant, let me do it anyway. And then we'll look at various other, like to every, one of the way to analyze simplices in many cases is to reduce the problem to graph. And we develop a little bit of machinery of evaluating, of studying mixing properties of bipartite graph, which are biregular, right? That's what we developed in the previous weeks. So let's look at them. They are relevant. And here the problems are not always completely trivial. Let's look first at B13, so one-dimensional spaces versus three-dimensional spaces. So let's study these two graphs. Now, in this case, the graphs is a bipartite regular graph. The degree is the same, right? And that's not difficult to compute. The number of points we have here, this is the one-dimensional spaces. We have cube to the 4 minus 1 divided by q minus 1, what we call n 4 over 1 cube. This is the number of subspaces, right? And here we have the three-dimensional, which is by symmetry, it's the same thing. It's 4 over 3, but it's exactly the same size. And the question is, what's the degree from here to here? It's really the question, how many, given a one-dimensional space in the four-dimensional space, how many three-dimensional space containing it? But given a one-dimensional space, the number of three-dimensional spaces containing it is exactly as the number of two-dimensional spaces in a three-dimensional space, because we can look at the quotient. So the degree here is exactly what we call 3 over 2, which is really 3 over 1 q. Okay, the number of two-dimensional spaces here. And here it will be the number of one-dimensional, so it's exactly the same. And now, if you want to look at the matrix, if A is the adjacency matrix of this graph B13, then B13, then let's, so we think of it as Z, it's a bipartite, so there is nothing here, and here we have some matrix B, and here we have some matrix BT. Right? That's exactly the kind of thing we did last time. And then here we see that, okay, so A square is B BT, here is BTB, 0, 0. And we want to compute the eigenvalues. Now, the eigenvalues of, okay, so let's see now what is BBT. So, or BTB, it doesn't matter. So we said that this is the A square is the adjacency matrix of the graph on the same vertices, representing going by paths of length 2. So I go from a vertex to some vertex and go to some other vertex. It can be maybe going back, and going back will be done in this number 3 over 2 or 3 over 1 cube times an identity, plus, now let's see in how many ways I can go from one to another. So if I have a subspace W1, and here I have W1 prime, both of them are of dimension 1, so they are contained in some two-dimensional space here, a unique one which contains both of them. And the number of paths I have here is exactly the number of three-dimensional spaces containing this specific two-dimensional space. Right? Is it clear? I want to ask myself in how many ways I can go from a one-dimensional space to a three-dimensional space and come back to a one-dimensional space. So this is really going from a one-dimensional space to some three-dimensional space containing W1, and also containing W1 prime. And they are different than each other, which means that, that this three-dimensional space must contain the two-dimensional space spanned by this one and this one. Okay? So given this and this, it gives me some vector space of dimension 2 here. Let's call it U. And the question is, how many three-dimensional spaces containing it? And that's very easy. This is exactly Q plus 1. Because we are inside a four-dimensional space. So the number of three-dimensional spaces containing a given two-dimensional space inside a four-dimensional space is exactly Q plus 1. Is it clear? I mean, these are easy considerations. Somehow you have to do it yourself once in a lifetime, somehow to get used to that. So this will be plus Q plus 1 J, J minus I, where J is the all I formula, right? So now let's do this computation once again. We did this kind of computation last time, but let's do it again to see what the numbers are coming here. So this is equal, so BBT is equal to Q to the, Q to the, so this is Q minus 1 divided by Q minus 1 times the identity. Okay, maybe let's write it better. As Q squared plus Q plus 1 times the identity plus Q minus I, Q plus 1, J minus I. So we take the J minus I there, so we are getting Q square I plus Q plus 1J. And now you remember we said, okay, so it means, let's see how B acts. So J acts as 0. We decompose the space. See, this is like, PVT is like looking on one side. I'm just looking on this side, right? BTB will be starting from here, but the eigenvalues will be just the same. Well, anyway, we know this is a linear algebra exercise, which I showed you or gave you as an exercise in one of the lectures before, that BBT and BTB always have the same eigenvalues. Maybe they are different by zeros. Well, in this case, I think they are even not different because this is both of them are of the same size. If they are not of the same size, then there might be some zeros in one of them which not in the other. So, okay, so what we have here now, so we have functions on that side of the graph which sum up to 0. The function which sum up to 0, the orthogonal complement of the constant, are vanished by J, right? J is 0 on these functions. So basically what we know that on that space in which J vanished, only this acts as Q squared. So the eigenvalues, most of the eigenvalues of A squared will be Q squared, which means that the eigenvalues of A will be, many of them will be plus or minus Q. Because Q squared will be an eigenvalue of J. Right, I'm doing it now faster than last time. I don't want to do in each computation, so all the details. Is it clear? But start with it's not clear. And now what will be the largest eigenvalue? We can guess. What should be the largest eigenvalue? Exactly the degree. Right? But let's see, let's be on the safe side and let's see that indeed that's what we get. Because you see, on constant functions, this is what we get on functions which sum up to 0. On the constant function, we get from here Q squared plus Q plus 1, the size of f. The size of J, right? If you take a constant function and you multiply it by 1, 1, 1, 1, 1, 1, 1, and you take 1, 1, 1, what you get is exactly as an eigenvalue the size of J. the size of J here is the size of this side of the graph, which is q to the 4 minus 1 divided by q minus 1. So this is equal q squared plus q plus 1, q to the 4 minus 1 divided by q minus 1. And what is the outcome? What should be the result? Don't compute. You should know.
Q squared plus Q plus 1.
It's q squared plus q plus 1 squared. Because this should be an eigenvalue not of A, but of A squared. Right? As an eigenvalue of A, I'm going to get the degree. But as an eigenvalue of A squared, I'm going to get the degree squared. Right? So this should be checked. At least regarding the degrees, it sounds correct, but you should hope that this is correct. I checked it. But I won't do it now. Better to be on the safe side. Okay, so let's do the more interesting and slightly more difficult case, just to show you what happens because so far we didn't see really, and I have a point, but I want to do one more example in details because I want I had a very nice success last time. I gave you a good exercise and three of you answered me. Two of them only last night and this morning, so I didn't have time to read it, but the one who sent me the first supposed to, yeah, but you will present it soon. And so I'll give you a more difficult exercise now today, but let me first point out something which is let me do one computation. Okay, and this is the G12. Okay, so now G12, okay, my notes I call it G12. Okay, let's say B12. So this is the one-dimensional against the two-dimensional. Now there are many more two-dimensional spaces than one-dimensional spaces. So this time is the first time that we see an interesting example of a bipartite graph, which is biregular, but really biregular, like the degrees are different. So let's see how many we have here. That's we already computed. The number of them is 4 over 1 cube, which is approximately q cube. And here we have 4 over 2 cube. Now, what is 4 over 2? That just, I don't remember if we did it last time or not, but think about it. How many subspaces you have of dimension 2? So you choose, you have for the first, you take a basis for such a vector space. So for the first vector, you have q to the 4 minus 1 possibilities. For the second basis element, you have q to the 4 minus q. And now, and this will give you all the independent sets of size 2. But many of them define the same vector space of dimension 2. How many vector spaces of dimension 2, given a vector space of dimension 2, how many bases it has? I have to divide this by q squared minus 1 by q squared minus q. Now this is not difficult to compute. It's q squared plus 1. The q goes out, and we get here q to the q minus 1 divided by q minus 1. So this is q squared plus 1 times q squared plus q plus 1. So this is approximately q to the 4th. So we see q squared plus 1 times q squared plus q plus 1. So you see that this is an unbalance, because this is something of order approximately q cubed, and this is something of order approximately q to the 4. Now let's see what is the degrees here and what the degrees in this side. So the degree here is given a vector space of dimension 1, how many vector spaces it has of dimension, how many vector spaces of dimension 2 containing are there, which contains that one. Which contains that one, right? This is the degree, how many two-dimensional spaces we have which contain a given W of dimension 1. So this is exactly as the number of one-dimensional spaces of the quotient. So this is the degree is 3 over 1 q, which is approximately q cubed. And on the other end, given a two-dimensional space, how many one-dimensional space are containing in it is exactly q plus 1. Okay? And that's okay, that's more or less what we expect, because what should happen is that the number of vertices on this side times the degree, what? The q. The number of vector space, the number of vertices on the left-hand side times the degree should be equal to the number of vertices on the right-hand side times their degree. So here we have something like q to the 4th times q, this is q to the 5th, and here we have q to the cube times q to the square, also q to the 5th. And in fact, they must be equal, not just approximately equal. So if you want, we can get an identity, really. The identity should say that 4 over 1 q times 3 over 1 q, which is is really equal to 4 over 2q times 2 over 1q. Must be true. Again, I don't check. It must be true, right? It's really nice identity. Okay. So this is the graph. But now let's understand. Now this time it's slightly more interesting story, because here we really get that you see the left-hand side is much smaller than the right-hand side. So this time we really have this is the other way. What? The other way around. Right? So it should be. Right, so here we have B and here we have BT, and they are really of different, not square matrices, but the eigenvalues of B, BT, say union, whoever you want to be, BTB, they can differ from each other only by zeros, and 0 is a great eigenvalue. No, it satisfies all the good conditions. It's a very small number, 0. In absolute value, it's still very small, especially in absolute value. But let's see what are the other eigenvalues. So it's enough to compute just one of them. So let's compute. Okay, so let's see. What will be like the going from the left side to the right side and coming back. So here we will go from a one-dimensional to two-dimensional and come back. So like the BBT will be the degree, right? Like the number of time to go and come back is the degree here, which is 3 by 1 q, the identity. And now the question is, in how many ways we can go from one dimension to two dimension and come back. That's actually easy. And this is plus, there is a unique way, plus j minus I. Okay, good. That's easy, and but I have a point I want to show something here. Okay, that's easy. So this is equal, so let's write it down. So this is equal, I'm continuing here, so this is q squared plus q plus 1 I plus j minus I, so this is q squared plus q I plus j. And again, so what are the eigenvalues? The eigenvalues will be the main j vanish on the functions which, I always think of vector as function, right? As a vector as function on the vertices. So it vanishes on the functions which sum up to 0 on this side, right? And the only thing which continue to live there is, so the eigenvalues are the square root of this, is the square root of q squared plus q, plus minus, and the trivial eigenvalues. What are the trivial eigenvalues? Now, let's see if you remember what we studied last time. What is the trivial eigenvalue now?
Plus minus degree.
What?
Plus minus degree.
But what degree? There are two degrees. You already forgot? If we have a bipartite, biregular graph, where the degree are k and l. So what is the trivial eigenvalues? Square root of k times l. Very important. Square root of k times l. Right? So it will be square root of k times l, and then plus and minus. So it will be plus and minus. Okay, let me put more space here because we need more space. It will be, eigenvalues will be plus minus square root of what? Let's write precisely. The degree of one side times the degree of the other side. What is the degree of one side? Is 3 over 1. 3 over 1 is q squared plus q plus 1, right? Is the number of subspaces of dimension 1 inside dimension 2, so this is 3 over 1 q, right? This is the degree from the left hand side, times the degree of the right hand side. So this is the eigenvalue. And 0 will come up. Okay, 0 will come up. If it won't come up on that side, on the small side, it's certainly going to come up on the other side. Why? Because it must come, right? If you remember the lemma, did I prove it or just gave it as an exercise? What?
You did prove it.
I did prove it, and from the proof you can see that really there are zeros coming up to the game if the sides are not the same. Somehow you have a map from small space to a bigger space and going back, and things which are not in the image, I think, are going to 0 in the kernel or something. One of them. The zeros certainly come into the game. So 0 will come up to the game. Anyway, okay, now, so this is, okay, let's see. So this is q cubed square root. So this is approximately q to the 3 over 2. And this is approximately q. Alright? Now, are these Ramanujan graphs? You remember I gave the definition of Ramanujan, right? Did I define Ramanujan graph in the previous class? I planned to, right? Did I?
You discussed it, but what does it mean in Ramanujan in biregular?
Right, very good. So I defined Ramanujan graph only for k-regular graph. And for k-regular graph, Ramanujan graph was the second if the largest eigenvalue, like the k-regular graph, the largest eigenvalue is k. The second to largest should be not less than 2 square root of k minus 1. So you might say, well, maybe that should be the general definition of Ramanujan. Like, take the largest eigenvalue and take the square root of it. K minus or whatever. And then If this will be the definition, then these are not Ramanujan. Because here the largest eigenvalue is something like that. The second largest is q. If I take square root of this, I'm getting q to the 3/4. And this is bigger. But this is not the right definition. So let me give, that's an opportunity. I did a computation in some sense in order to enable me to explain you what is the right definition of Ramanujan bipartite graph. And this is the preparation for us to the notion of Ramanujan complexes in the higher dimensional case to understand where the notion comes from. I will not prove what I'm saying now, but well, because I didn't really prove also the Lombopana. At some point maybe we will prove the general Lombopana, which will include all of them, so I don't want to do it in too many special cases. So let me explain. So recall that K regular graph is a finite K regular graph. Say connected, finite, connected K regular graph is called Ramanujan if every eigenvalue of it always mean of its adjacency matrix satisfies lambda either plus or minus k, or lambda is at most 2 square root of k minus 1. Where this number 2 square root of k minus 1 come from? So such, let's call it x. Such x is covered by in the sense of algebraic topology, the universal covering of x is covered by the k regular tree tk, which is this is an infinite tree, such that the degree of every vertex is exactly k. And you know, it goes forever. And this is the universal cover space of a k regular tree. Now, what is A? What is the adjacency matrix of the tree? So we can really write x as tk divided by gamma, where gamma is really pi 1 of x, the fundamental group of x acting on tk. Right? I hope everyone is familiar with basic algebraic topology, right? That's the kind of thing. If you have a topological space, you can talk about its universal cover. In this case, universal cover is exactly 3. And now here one can really build it by hand. You don't need fancy algebraic topology. You can really kind of define it by elementary means somehow to show what to talk about that. But now, but here's the point. Look at the operator A from L2 of tk to L2 of tk, which defines by, so L2 of tk means functions L2 on the vertices. So these are functions, like complex functions, such that the sum over the vertices square is finite. Right? So this is an this is like an operator between two Hilbert from an Hilbert space to itself, and I can talk about its spectrum. And the spectrum of this operator, so this is a non-trivial exercise. I mean, you have to know a little bit about the theory. One can do it combinatorially after one understands the meaning of this. But at this point, I don't want to worry about that. I mean, I'm just telling you this is a story in order that you will understand why I'm going to define differently than you expect the Ramanujan for bipart, right? The spectrum of this is minus 2 square root of k minus 1 to 2 square root of k minus 1.
You normalize?
What?
You normalize the...
No, I didn't normalize. I mean, I could, but I didn't, so let's not normalize. This is the spectrum. So, now, okay, this is the spectrum of this. Okay. Now, what is now the definition of Ramanujan graph? Basically, the way you should really think about the definition of Ramanujan graph is in the following way. We have the universal tree. The universal tree is kind of the ideal object which covers all the k-regular, all the finite k-regular graph. And in some sense, well, you all know now that the expander, that bounding the spectrum is also related to expander. In some sense, that we can make precise, is that the infinite tree is the best expander. Like if you take a subset of it, a finite subset, and you look at its boundary, it's expand in the best way somehow. But we cannot implement the tree in the real world. So if we want to implement in the real world as a k-regular graph, like there are two trivial eigenvalues, k and minus k, which are kind of enforced on us. The k is always enforced on us, it's always. And minus k depends if it's bipartite or not. So in some sense, these are the trivial eigenvalues. And one really have to understand in the general situation what does it mean, the trivial eigenvalues, but they are kind of trivial eigenvalues. And what we want is that all the other eigenvalues, the non-trivial eigenvalues, will be in the spectrum of the infinite tree. That's what we asked, right? The definition of Ramanujan says that either we are talking about the two trivial eigenvalues, and if not, you are in the spectrum of the universal cover. And this is the correct definition of what does it mean for a graph to be Ramanujan. Now, why I say that this is the correct definition? Because last time I also presented to you a Lombopana theorem. You remember Lombopana theorem? Lombopana theorem told us that if you want to bound the eigenvalues of k-regular graphs, of an infinite family of k-regular graphs, you want to be able to do it better than this 2 square of k minus 1 for an infinite family. I stress the point, you remember, that for one graph it might be possible. For example, we saw such a graph. What was the graph?
The complete one.
What?
Complete.
The complete graph, or better and more interesting, the line, we did some computation, right? The line versus points of the projective plane, you remember, the largest eigenvalue was q plus 1, and the others were square root of q, which means that they are less than 2 square root of q. Right? If the degree is k is equal to q plus 1, then I should bound by 2 square root of q. Now, this is not a contradiction, I stress that point. This is not a contradiction to the Lombopana theorem. Why? Because the Lombopana theorem is about infinite families of k regular graphs for the same k. Is it clear? Now, what would be the definition definition of a Ramanujan graph for definition? Or maybe first there will be a definition plus a lemma immediately. Definition: if x is any finite graph, not necessarily regular, and T its universal cover. It's also a tree. That's easy to see that it should be a graph, but a graph which is simply connected is a tree because there are no loops, right? If there are loops, it's not simply connected. right? Universal cover should be simply connected, and it should be connected, and this really means a tree. And then we can talk about, then X is called Ramanujan if all eigenvalues of X are either trivial, so I have to explain in a minute what does it mean a trivial, or in the spectrum of the adjacency operator of T. This is the right definition. Why? Because there is an Alombo-Pana theorem. Alombo-Pana here, well, this is actually a result of Yossi Greenberg. In this case, it's really a theorem of Greenberg. Unfortunately, never been, well, actually, in this case, it doesn't matter. It was published in his thesis here at the University 20 years ago in Hebrew, never appeared in the literature, but nowadays in the literature there are more general results than that. So it's already in the literature in a different way, but Greenberg was the one who proved this version. And this is that this is the best bound you can opt, I'll write it in a little bit informally, you can opt for an infinite family covered by T. So it's like, what will be the analog of K-regular graph that we talked before? An analog of K-regular graph that we talked before will be all graphs covered by the same tree, T. In the case, if this tree is the K-regular tree, then the graph, the finite graphs covered by it is exactly the family of all K-regular graphs. Now I have any tree. Then I look at all the finite graphs covered by it, and they have two trivial eigenvalues. Now, and all the possible trivial eigenvalues, all the others, well, and we call it Ramanujan if the others are in the spectrum of the cover. And I said you cannot get a better bound than that bound. Now, in general, what is the trivial eigenvalue? In general, the trivial eigenvalue is the so-called Ferron-Four values. You take the adjacency value, you take the Ferron-Four values eigenvalue, and it can appear and its minus can appear. That's a similar story. So if you know this little theory of matrices, fine. If not, I don't want to spend time on it. But I want to talk about the specific. Okay, the truth is that I'm a little bit hiding. There is a little point if somebody wants to work out a little thesis about that, I don't know, or check this. There is a slightly, in the literature, there is slightly two versions of the definition of Ramanujan, which not clear to me that they're equivalent. You can talk about the spectrum of that every eigenvalue downstairs is inside the spectrum upstairs of the tree. That's one way to say it. Another way to say it, that every eigenvalue. Now, what is the norm of such an operator? The norm of an operator A is the top of the spectrum. The norm of A is this 2 square root k minus 1. But usually in the literature we say that every eigenvalue is either the trivial one or it's less or equal the norm of A. But I don't think, and I don't know, that for every tree, the spectrum is continuous span. It's really like an interval. what happens, and I think there are cases, even in the biregular, that there is that the spectrum is a union of two intervals. Right? So you can give two different definitions of Ramanujan. One is that all eigenvalues are bounded by the norm of the adjacency matrix, of the adjacency operator on L2 of the tree. Or you can say that you are really inside the spectrum, which would be a stronger property. Okay? So now let's talk about now let now T be TKL. If you take TKL as your bipartite, as your infinity, then TKL, the norm of the operator of TKL is equal to square root of k minus 1 plus square root of L minus 1. Which of course at k equal L, we are getting the old results. By the way, what is TKL? You understand, TKL is the kind of graph that is the tree that the degree here is 3, and now let's say the degree next is 4. And then again, now it will be 3, and the next level will be 4. It's like it's a bipartite. It's a bipartite tree that the degrees are K and L, K and L, K and L, K and L, right? Now, so what is the definition? Okay, so now, well, to be honest, I don't quite remember because it came to me only now when I was doing it. But I think that the spectrum of these three is not continuous. Shachar, you remember? What the spectrum? I'm sure that we looked at it many years ago. What? It's not connected. So in the definition of Ramanujan, you can ask yourself, you can give two different definitions of what does it mean for a biregular graph to be Ramanujan. Right? You can claim that all the eigenvalues are bounded by this number, or they are really in the spectrum. And I'm not sure if this is different. Anyway, what I want to say, that what we found now, so all this was kind of a long remark in order to explain that what we discover now, okay, now let's go, after all this big story, let's go to the example we computed. And I claim that this is Ramanujan. Why? So you see, before that we thought that maybe it's not Ramanujan because the largest degree is q to the 3 over 2. The second one is q, and it's not square root of it. But being Ramanujan for a biregular graph, should be less than this number. So now I claim that this B12 is Ramanujan. Okay, let's check why. Okay, all this was in order to make this claim. Why this is Ramanujan? So let's recall. What was K in this case? In this case, K, it's still written there, I hope. Right? It was like 3 over Q. 3 over 1Q, which is approximately QQ. Right? And N, a Q squared. And
K
N,
and L are written there. They're
What?
the product. Say eigenvalue plus minus square root of K times L.
here they are, right. Okay, so what we need, okay, so yeah, so this is K and this is L, right? So K minus 1, so what we need that the eigenvalues will be less than square root of Q squared plus Q plus square root of Q. That's what we need in order to check if B12 is Ramanujan or not. And the eigenvalues are what? They are square root of this, so this is less than that, and 0. So this is fine, and this is the trivial eigenvalue. So they are Ramanujan. Okay? And the question I want to raise to you, and the exercise, but this is exercise which I don't know to solve myself, and I don't know. I don't think it's a problem for people not to compute, but I have the feeling that if we will look, so fix n, and look at the graph Bij, namely I-dimensional spaces versus J, let's say I less than J, versus J-dimensional, it would be nice to know that they are all Ramanujan. So one should, now we understand what we mean here by Ramanujan. It's taking the degree. To compute the degree, to compute the order of the degrees is not difficult. To compute the eigenvalues is slightly more difficult story. I mean, like, I more or less cover all the trivial cases. Now, well, if I is 1 and J is something, then it's not so difficult. If I think if I or J, I'll give you an hint, or maybe I shouldn't give you an hint. Maybe, I mean, what I think should be done here, but maybe, no, maybe I should, well, maybe let me show you. I'll take another few minutes and then we'll take a break and then you will present your, okay? Let me show you that there is some we did some trivial calculation, but there is some interesting, not so trivial consequences, which I'm not going to push here, but let's look at the following graph, for example. If I'll ask you directly, then this is I think, a non-trivial exercise, but somehow I think it follows from what we said. Look at the, again, let's look at f cubed to the 4, and let's look at two-dimensional versus two-dimensional spaces, but the difference